second row, CSTR the second column. So the equation is tau 0 is equal to CA, well, it should be, yeah, CA in minus CA out over minus RA out. For first order reaction, what is minus RA? And it's out, so I have CA in minus CA out over K CA out. And now I solve this set of equations. So I multiply through, I have K tau 0 CA out. I'll bring this to the other side of the equation, K CA out equal to CA in. So what I have here is I can factor out the CA out. I have CA out divided by CA in. It's 1 over 1 plus K tau 0. So in CSTR, we have that the ratio of the outlet to the inlet, where A is a reactant here, is 1 over 1 plus K tau. The outlet concentration is smaller than the inlet concentration if there's a reaction going on. That's because K tau is greater than 0. We can see the denominator is smaller, is larger than the numerator. So this all makes sense. Notice that when you solve a CSTR equation, if you look at any of these equations, the CSTR, they're algebraic equations. There are no derivatives and no intervals in the CSTR equation. So it's fairly straightforward to solve, usually. In contrast, the plug flow, the plug situation involves taking an integral. Sometimes it's easy to integrate, sometimes it's not. I'm going to do the same case for the plug flow. So there I have, again, I go to the middle one, the second row, third column, and I'm going to integral from CA out to CA in. dCA over minus RA. So now minus RA is a function of CA as opposed to just being CA out. CA out, CA in, dCA, and KCA. Again, I multiply out by K. And I integrate this, and I get the log CA in and CA out. Let me just finish the algebra, and then you can ask a question. I multiply by minus 1, that flips these. And I take the exponential, I have CA out over CA in is equal to e to the minus K times 0. And by the way, does this remind you of anything? Have you ever seen this? Something that we've done this before? First order. What kind of reactor? Batch reactor. So you can notice this looks just like the batch reactor. And that's if you compare the constant density, the second row, third column with the second row, first column, you could notice that those two equations are exactly the same. The only difference is instead of in and out, we have time t and time 0. So if RA is the same, it's no surprise that we get the same answer. And there's something a little deeper behind that we'll discuss.
Okay, so for the CSTR case, why do you use the steady state to
I don't understand the question.
Okay, so the result here that you get is because you say DC equals D0, right? So
what we did is we derived the general performance equations for the CSTR and the plug flow reactors. We did that for the unsteady case last time. And then we specialized it in a steady state. So the idea here is, before we consider more complicated cases, we like to consider the simple case first. So the simple case is steady state. That doesn't mean that the unsteady case is not interesting. But typically, if you're trying to produce a product in a plant, and you want to produce a lot of it, because it's a big money maker. You just discovered the new Viagra. And you want to make it as fast as you can and sell and make as much money as you can. First, you want to use a continuous reactor rather than a batch reactor. Because a continuous reactor, you turn it on and presumably it just runs forever. Where forever means until something goes wrong. Batch reactor, You put stuff in, when it's used up, you gotta start cleaning it out, start all over, not efficient. When you can achieve steady state, it's generally preferable, usually, because you have less problems. If the reactor is running at steady state, then presumably you have stuff coming in, reactant coming in, product coming out, very predictable. If it's at steady state, you have the same product coming out all the time, and it's very easy to run your plant. If you run your reactor in an unsteady fashion, then what comes out is unsteady, and you really have to pay attention. And it's not always clear. In many cases, first, it's much easier to operate, and often you get better time average performance with a steady state reactor than unsteady. Now, of course, whether you reach steady state or not is a much more interesting question, which is, we're not up to that yet. Other questions? Okay, now as I mentioned, when you look at these systems, the plug flow reactor and the batch reactor, they look very similar, those equations. Instead of time 0 time t, you have in and out. And other than that, they're exactly the same equation at steady state. I'm sorry, at constant density. That's not true in the general case. What's the difference in the general case between the batch and the plug flow reactor? So want to look at the equations? What's the difference between the equations? In the first row, volume 1, full sentence. A full sentence. Do you know what a sentence is? Does anyone know what a sentence is here?
In the case, in the first case, the first box in the general case for the batch reactor, the volume varies, which is why it's
Varies with?
Varies with concentration.
It can also vary in the plug flow reactor. The density can vary. The density can vary. What's the difference between these? Look at the equations.
For the case of the batch reactor, the volume can vary in the case of the plug flow reactor.
But the density can vary in both cases. The volume is a representation of the density. What's the difference between the batch reactor and the plug flow reactor? The equations.
Concentration. Between the concentration and
Raise your hand.
in the plug flow reactor, you have the constant concentration is there, and there's a constant mole concentration in the general case for the batch flow. Which means, so if you change the density in the plug flow, the concentration changes proportionally with it. Okay?
It's much more straightforward.
The batch is performance will determine the time of the plug.
So that's always the case. That's not what I'm looking for.
In the plug flow, B is at B naught. That's why you can put NA naught over B naught, and that makes CA naught.
And in the batch?
In the batch, D is there, so it's not equal to B naught.
Okay, yeah, that's exactly what I'm looking for. If you notice, in both cases, the density can vary. If I have a non-constant density reaction, it can vary. However, in the batch reactor, that variation is inside the integral. In the plug flow reactor, that variation is not in the integral. In the plug flow reactor, we do not use the actual density. It turns out we use essentially the density of the reference state, the volume at the reference state. Now, that's the way it worked out when you derive the equations. It's not that one is wrong and the other one's right. It's the difference between the reactor types. However, at constant density, if I have a constant density reaction, then there's no difference. So, in a constant density case, we can think of something very interesting. We can think of, okay, let's just draw the two reactors. Here's a plug flow reactor, and here's a batch reactor. In a batch reactor, the assumption is the reactor is well mixed. There's no difference in the concentration anywhere in the batch reactor. But the concentration is only a function of time. It doesn't vary with anything else. In a plug flow reactor, what do we assume? What are the mixing assumptions in the plug flow reactor?
No mixing.
No mixing in what direction? In Z. There's no mixing in Z. How about in R and phi? In the cross section? Raise your hand. Well, then I can have variation in R and phi.
You could mix in the R and theta.
In R and theta, I assume that there's no variation in concentration, whether by mixing or by magic. But there's no variation in the plane. So the concentration is the same everywhere in the plane, in any cross-section. The concentration does not depend on R or phi. The concentration only depends on Z. And there's zero mixing in Z. So zero mixing in Z. But full mixing, I don't even want to call it full mixing. I would call uniformity in R and phi. So there's no variation in R and phi, either because I mix there or just because that's the way it is. Usually we emphasize the zero mixing in Z. Okay, so what does this imply? What can we picture here? At constant density, we said these equations look very much alike. Well, picture the following situation. Let's take one cross-section that's entering the reactor, that's entering the flow reactor. One cross-section. That cross-section, because there's zero mixing in C, doesn't see the cross-section right in front of it, and doesn't see the cross-section right behind it. As far as it's concerned, as soon as it entered the instant it entered the reactor, someone flipped the switch and turned the reaction on. And as it moves through the reactor, some point later it's over here, it still doesn't see anything in front of it or anything behind it. Doesn't see means it doesn't mix with anything in front or behind. And at some point it leaves the reactor, and all of a sudden the switch turns off. How long did it take to go through the reactor? How long did it take to go through the reactor? Well, if it's a plug flow reactor, the velocity is uniform. Velocity doesn't change. I have a certain length of the reactor, L. And I have a certain velocity, U. Let me call it W, because it's in the Z direction. So the amount of time it took to go through the reactor is equal to L over W. So if I multiply by the cross-sectional area and divide by the cross-sectional area, L, what is the length times the cross-sectional area? Volume. And what is the velocity times the cross-sectional area? It's the velocity times the cross-sectional area. So length per unit time times a length squared. What are the units? Huh? Volumetric flow rate, V. And what do we call big V over little v? What do we call big V over little v? Did no one look at their notes? Did you pull this out? So you don't look at your notes before that?
Space time.
Space time. Tau zero. So when I have a constant density system, at constant density, this is all under constant density, the time it takes for a cross-section to pass through the reactor is tau zero. So the identity of those two equations, what is that telling me about this cross-section? Volunteer? This requires thinking. What is the fact that those two equations are the same in this picture, what does that tell you about the cross-section at constant density?
It's like a batch reactor?
Each cross-section is exactly a batch reactor. What happens in a batch reactor? There's no positional variation in concentration. There's no positional variation in concentration. The concentration only varies with time. Well, here the concentration varies with Z, but Z just scales with time. Z is just velocity times Z is just WT, velocity times time. And the equations are exactly the same. So that tells me for a constant density system, each cross-section is exactly a batch reactor, and that's why the equations are the same. And the only difference is I have to convert T and Z are equivalent in this way. As long as W is the same everywhere, they're exactly the same. And that will have implications later on. Why does this go wrong for a non-constant density system? See if we have someone thinking. Why is this not true for a non-constant density system? What happens if I have, say, volume expansion? The density goes down with the reaction. Well, you can think about that while I go on and do the next example. All right, let's just do another example for CSTR. CSTR, steady state, first order, linear volume expansion. So again, it's the same equation, but now I have tau is equal to CA in minus CA out divided by KCA out. That's the same, but I have linear volume expansion. So in linear volume expansion, I have CA is equal to NA over V. What is NA in terms of XA?
NA 0 times 1 minus XA divided by V0 times 1 minus XA. No? Oh, epsilon times XA.
What's the sign here? Plus. And this is CA0. Okay, so this becomes, so let's just notice, I'm sorry, this is the wrong equation. This is the constant density equation. I should be using the linear volume expansion equation. Linear volume expansion is the third row, CSTR, is CA0, XA out minus XA in divided by KCA out. Okay, so I still needed the CA out, so this is equal to, so I'm going to multiply by K. So I have K tau 0 is equal to X out minus X in over CA out, where CA out is the CA 0 times 1 minus X out divided by 1 plus epsilon A X out. So I just plug this in for CA out. I cancel the CA zeros, and now I have to multiply everything out. So let's bring the denominator of the denominator into the numerator and multiply it out. So I've got X out minus X in plus epsilon X out squared minus epsilon A X out X in. And this thing is equal to, I multiply this out, K tau 0 minus K tau 0 X out. Remember, this is an algebraic equation. And let's remember what's typically unknown here. Either tau is unknown or X out is unknown. So I'm going to look at the case where I want to calculate X out. So let's try to calculate X out. So if tau naught is given and X out is unknown, then I have to solve this equation for X out. If X out is given, if the specifications are given, and I want to calculate tau naught, well, here I have it. I just divide by K. It all depends what the question is. So here I'm going to guess, I'm going to look at the case where I have to do some algebra, and that's the case where X out is unknown. So notice this is a quadratic, everything else is known besides X out. So this is a quadratic equation. So I have epsilon A X out squared, and then all the terms that have an X out. So then I have a plus X out. And what is that multiplied by? Well, here's a term, there's a 1. Here's a minus epsilon X in. And here I have a plus k tau. For this term. And now I have the constant term. So then I have minus k tau naught minus x n for 0. So here I have a quadratic equation in x out, and I can solve that quadratic equation. And, by the way, this is a plus. And let's just notice, let me rewrite this, 1 plus k tau minus epsilon a x in. Let's just notice I have xa out is equal to minus b, so I've got minus 1 plus k tau naught minus epsilon a x in. Plus or minus the square root of this thing squared, 1 plus k tau naught minus epsilon a x in. Minus 4ac, so I have plus 4 epsilon a k tau naught plus x in divided by 2 epsilon a. Why did I bother writing that out? Why did I fuss? I assume, I hope, you know the quadratic formula. The reason I wrote it out is because xa out had better be positive. So I just want to convince you that it's positive because here is a minus something, here is plus the square root of that thing squared. So if this was 0, we could just add up to 0. But I have a plus here, I'm adding something positive to it. So it says the thing here that I'm adding, obviously I only keep the plus sign because I can't have minus x's. The thing I'm adding is bigger than the thing that's negative, so this will definitely be positive. You also should verify that this is less than 1. X out, gotta be less than 1. I'll leave that to you. Any questions on that? Let's do another case, another one. This is sort of straightforward, but I just want to give you a little exercise in doing these. Let's look at a second order reaction constant. So here I have tau naught is equal to Ca in minus Ca out over what is the minus Ra for second order constant density reaction? Yes? Hello? Can I wake you up? Is it a shock to you that since I went this way, that you're the next one who's going to get a question? What is the rate of a second order reaction? Just say it louder. It might have been right. I just can't hear you.
Minus k times CA to the second.
CA to the second power. But that was the plus the rate, minus the rate gives me k CA squared. All right, so this again is going to give me a quadratic equation. I have k CA out squared tau naught plus CA out minus CA in equals 0. That looks like a quadratic equation to me. So I get CA out equals. So next person, please apply the quadratic formula.
Negative CA in, no wait, negative 1 plus or minus 1 squared, square root of 1 squared, minus 4 is a k tau 0 divided by times negative c, negative 1.
Times negative 1? So you don't know
Yes,
the quadratic
positive.
formula.
Divided by,
Can you please fix it here and see if you know the quadratic formula?
Minus k tau minus 4 minus times.
I have to go around the room to get the quadratic formula, I give up.
Times CA and divided by 2 times k tau naught.
And what about the signs?
You want it to be positive
Positive. Why is that?
because the right side you want it to be, it's going to be greater than minus 1. so you want.
Why do you run off the positive sign rather than the negative sign?
Because if you minus and minus, it's still negative.
And what's wrong with that?
You can't have
You
negative.
can't have negative concentration. Okay, so I think you can see that these are fairly straightforward. Let's try some more examples with the plug flow reactor. Another example of the plug flow reactor. Let's see, did I have any other examples I wanted to do there? I think you get the idea. Let's try a plug flow reactor, first order reversible reactor. Constant, let's try constant density. Constant density. Let's do with constant density and then without constant density. No, let's just do it without constant density. See how nasty it gets. First order reversible.
First order,
Linear volume expansion.
reversible.
So let's look at A goes to little r, big R. But the kinetics are first order. So even though there's a little r here, I'm assuming that the reverse reaction is first order. Remember, there's stoichiometry and kinetics. So here I'm assuming the stoichiometry, I have little r moles of molecule species R, but I'm assuming that the rate is first order. Okay, so I have A and R, and let's note that Na is equal to Na0 times 1 minus Xa. Is Na0 minus Na0 Xa. Where this is the moles of the reference state, this is the moles now. So this is the change in moles from the reference state. It's the amount of moles used up from the reference state, assuming. So, and then I have similarly NR is equal to NR0, 1 minus XR is equal to NR0 minus NR0 XR. So this is number of moles, well, change in moles of A from reference state. And this is the same thing, the change in moles of R from reference state. As I told you, we have a certain vector here. If I have the vector with AR, then what is the component, say if I look at the forward reaction for A? What is the first component? Minus 1 for A and plus R for R. What we said was that Na0 Xa, the way I always get this right, if I divide by this number, I set that equal to NR0 XR, and I divide by this number. They're going to be the same. I always have to divide, not multiply. And notice there's a difference in sign, because this is a reactant, this is a product. When this goes down, this goes up, vice versa. So that tells me that NR0 XR is equal to minus R. So this is equal to NR0 minus R Na0 XR from this equation. That is, this is equal to NR0 plus R Na0 XA. And I can factor out an Na0 times M plus Rxa, where M is defined as NR0 over Na0 at the reference state. So here I'm assuming that my reference state has both R and A. If it doesn't, then you have to do things a little differently. Don't worry about that right now. So Ra, since it's a first order reaction, is minus A1 CA. And what's the second term? It's a first order reaction. Exactly. The rate of production of A.
K plus K2 and
CR. Are there any other coefficients here?
CR.
Are there any other coefficients here?